1996, the Ariane 5 rocket launched. The flight control software was working to keep the rocket orientation vertical and manage the horizontal velocity. 37 seconds into flight, an unsafe conversion of a 64-bit float to a 16-bit signed integer overflowed and caused a hardware fault in 2 redundant inertial navigation systems. Both of these systems failed at the same time due to the same software problem, which led to cascading hardware issues, or to cascading faults, leading the rocket to veer off course and self-destruct. In other words, a simple integer overflow caused $370 million to vaporize in 40 seconds. Luckily, surely aviation companies have learned from this incident and provably avoid overflow, right? Okay, maybe not. You have to restart your Boeing 787 every 51 days to avoid potentially catastrophic misleading data from being shown to pilots. So the bad news is that since the 1990s, firmware has gone everywhere. There's software controlling your car, controlling your heart, and maybe in the future controlling your brain. And all of these systems are going to have wireless access. So anyone can try and hack into any of these devices. So we really need reliable firmware and secure firmware. Otherwise, software higher up in the stack has no chance of being secure and of being correct. So my name is Samir Rashid, and I'm going to talk about how the Talk operating system eliminates many classes of bugs that plague other operating systems at compile time, and how we're working to use lightweight formal verification to further get stronger guarantees about the correctness of Talk. But before we see how TalkOS is safe, we need to understand what kind of issues we see in system software. And we need to understand our threat model. So if you look at the faults that you find in the Linux kernel, you'll see that not all faults are the same. You'll notice 2 things. One thing is that you find way more problems in drivers than the rest of the kernel, and also these problems tend to be related to memory issues. So if we can find a way to prevent these 2 things, then we're actually preventing the vast majority of problems that you see in the wild. So let's try and classify the kinds of bugs we might see in general. So you could have problems where you're not checking the length of a buffer, or you're dereferencing a null pointer. There's many ways to introduce undefined behavior in C. Drivers could have some problem, and that might take down your whole system. You could have deadlocks or data races in the kernel. And maybe more complicated, the kernel developers might not understand how some subsystem works, or you might call a function wrong, which would cause a logic bug. This may not induce a crash. You may never be able to induce a crash based on incorrect behavior, but your program is still going to be doing something that you don't expect. And in fact, people might be intentionally trying to do this, and particularly like abuse your system with malicious attacks. So we have a spectrum of bugs that range in difficulty to fix. Maybe these bottom ones are harder to fix. But let's look at how Talk works to mitigate these threats. So first I'm going to give an overview of TalkOS and its design, and then I'm going to share our work applying formal verification to Talk. So Talk is an operating system for low-power embedded devices, and it enforces isolation and safety between processes. Talk is used as a research platform at several universities, and it's a general-purpose OS, but some use cases you'll see it can be used as an OS for wireless IoT devices, and it's also used as a root of trust. So it's used in industry by Google and Microsoft. For example, every modern Chromebook is running TalkOS in its security processor, and Microsoft's new Pluton processor is running TalkOS on die. And TalkOS also backs a few major open source projects such as OpenSK and OpenTitan. So let's take a look from the top. How do processes work in Talk? Processes are isolated using hardware. So on ARM chips, we have an MPU, which allows you to specify ranges of addresses that are going to be accessible in user mode to the process. So of course, the thing to note is that we don't have full MMU. We don't have virtual memory. Everything is physically addressed. And processes can be written in any language, and these can be loaded and restarted at runtime. And another thing you'll notice is that here at the bottom, the stack is growing downwards towards the end of the memory, the accessible memory. So that means that stack overflows are going to cause the kernel to take control if it traps into the kernel, rather than the stack overriding process memory or even overriding other processes' memory. So that should only affect this one process rather than taking down the whole system or having weird behaviors. Next, below this, we have capsules, which are basically drivers. These drivers are written in safe Rust, and they're compiled with the kernel. So that means you can choose which capsules you want to trust when you're building your system, limiting the amount of exposure you have to third-party code. Also, capsules don't have full access to kernel functions. Talk has a privileged system of capabilities which is enforced through the type system. So basically this means that when you're making a capsule, you'll construct some empty struct, and this might be like networking access. And you give it to this capsule, and then when this capsule is trying to call some privileged code in the kernel, it's going to provide this type and say, I have access to this function, and this can't be forged. So the benefit of this is that if a capsule tries to access a function it can't, that's going to fail type checking, and this will fail at compile time. Another benefit of this is that there's no overhead, because all the checking is done by the compiler. So almost all overhead of runtime checking for privileges is eliminated, and there's no memory overhead for this, because it just gets compiled out. Another interesting thing is that capsules and the kernel have complete static memory usage. So you know when you're compiling exactly how much memory needs to be reserved for the OS. But if a capsule needs to service a request system call from a process, then it can use memory that's within the allocation of the process. So that's the grant region at the top. So if the capsule needs to store some internal data structures or it's passing buffers to the process, then it can store memory there. And that's not accessible to the process, but it is accessible to capsules in the kernel. So that means if a process is sending a bunch of requests and is exhausting memory, then that will only cause its own data or its own self to get hurt rather than taking down other processes and exhausting the entire system. So in summary, you can think of capsules as not malicious, but they're allowed to have bugs, and this won't take down the system. Buggy user space drivers cannot compromise the system integrity because the type system isolates it from the rest of the kernel. So lastly, we have the kernel, and the kernel is interfacing with hardware, which is fundamentally unsafe. So we do need to trust the kernel. So we really care about correctness here. So the kernel is only a few thousand lines because a lot of the complexity gets pushed to capsules. The kernel, because the hardware is fundamentally unsafe, we do have unsafe Rust in the kernel, but most of it is memory safe. So let's take a look at the problems we outlined. So with Rust, we've solved some problems for free. Now we know Rust is memory safe. You're not going to get buffer overflows. And undefined behavior is now explicit and restricted to the kernel because you have to wrap undefined or blocks which could have undefined behavior with unsafe in Rust. Next, the TOX architecture encapsulates the problems that drivers could have using capsules. And also, TOC completely bypasses concurrency and locking issues because the kernel is not concurrent. Everything the kernel does is run to completion. Okay, and then we're left with these two really difficult issues. How do we get rid of these last two? There's not great methods for solving these so far. Using safe Rust and disallowing external dependencies is going to restrict the amount of logic bugs you can have, and it's going to restrict your attack surface, but bugs can always get through even the most scrutinized open source projects. And same with attackers. You could have highly resourced attackers who are looking for slight misbehaviors in your program and trying to exploit that, such as what happened to XZ. So we have solved maybe by percent most bugs, but you can still have a lot of bugs. If you look at the patches to Linux memory allocation code, 90% of it is just changing existing code. So it's dealing with optimizations, code maintenance, and bug fixes. Only 10% of patches are for new features. And if you do look at these bugs in the kernel, if you measure the time from their introduction to the time they get fixed, their lifespan is about 2 years on average. So these bugs are extremely difficult to find. And so that means during this time, you're just waiting for someone to find them and exploit them. So that's not great. So now I'm going to talk about how we're trying to use lightweight verification to get rid of these last two issues in talk. So before we do a demo, what is formal verification? Essentially, you're trying to prove that your program is going to behave how you expect it to. So that means you could prove some like low-level properties, like your code doesn't panic, or it could be high-level properties, like your program is not going to leak sensitive data, or it's crash safe. So I'm going to be showing a tool called Flux. Flux is under active development and allows you to refine variables in Rust. So you might have heard previous things about formal verification, that it's so slow, you'll have to rewrite your code, or that you need a PhD in formal methods first. So I'm going to make the claim that these are not true. Flux only takes a few seconds to run. It allows you to incrementally retrofit existing code, so you're not going to have to rewrite your entire code base. And you're going to see how easy it is. So first, let's take a look at this function have. So I'm writing in Rust because that's what Flux uses. We have this type signature at the top. You can see it's taking an input called x. This is a signed 32-bit integer, and it's returning a 32-bit signed integer. And all the function is doing is dividing it by 2 and returning it. So we want to think about, or first let's add some boilerplate. When you're using Flux, the way you develop is you're basically adding type signatures to your functions. So I've just added this boilerplate which doesn't say anything. It's just copied the same typed signature. All we know is that we're taking a 32-bit signed integer and returning another one. So first we need to think about what would it mean for half to be correct. So intuitively I'm thinking that if I'm dividing a number by 2, then it should be less than the input, right? So I can name this output v. It doesn't matter, it's just a name. And I want to say v is less than x, where x is this variable right here, which is the input. And Flux immediately complains, right? It's going to say this, it's underlined this v and says, this condition cannot be proved. And if you think about this, okay, well, I forgot that x can be a negative number, so actually, if you pass in a negative number, that's going to be smaller than the output, because the output is a smaller negative number. So let's just say that actually this number should be positive. Or this number should be non-negative, right? So it should just be greater than or equal to 0. Well, that's still wrong, because if x is 0, then that's not smaller, or that's not bigger than the output. So if we do make that x is greater than 0, then we've solved this. So that's basically the process for developing. And we've seen that here, we basically have a precondition, which is saying what would it mean for it to be a valid input, and what invariance should or what logical constraints should the output hold. So there's two things to note. One is that this type signature is a subset of the Rust type signature. So all positive I32s is a subset of all I32s. And same with this. So when you're reading this code, you can just ignore the Rust type signature and pretend like you're just dealing with types. Of course, this is because Flux is not built into the Rust compiler, so we're just adding these annotations. So I would read this function as have takes a positive number and returns a smaller number. Of course, this number is still positive, or this number is non-negative, but we haven't expressed that. So we saw that Flux is going to surface issues by underlining it here in the post condition, but we haven't seen what it does with preconditions. So that's because we're not actually calling have anywhere. So if we call have with maybe 10, then this should work, right? Flux is happy. But if we call it with minus 10, then it's going to complain that, or it's underlined this, x is greater than 0, and says this was not proved. We've violated this constraint. So you can express whatever constraints you want in these type signatures. So this could be anything that's meaningful to your program. I've just given a simple example here. And maybe this looked a little bit simple, so let's look at another example, which is absolute value. So we have another function here. Intuitively, this looks right to me. If I'm taking the absolute value, all that's doing is flipping the sign on the number. So if I have a positive number, that's fine. But if I have a negative number, then I want to get rid of the negative sign. So let's try adding a type signature for this. So what would it mean for absolute value to be correct? We can think about this again. Maybe we want to refine this output to be a positive number. That's definitely true. So that will take care, that is correctness for negative numbers. For negative inputs, we want the output to be positive. And for positive inputs, we want the value to stay the same. So we could express that by saying x is, or this output, v, is going to be greater than or equal to the original value. So I've added that here. We haven't refined the input, and we've refined the output to say that the output must be positive, and it must be greater than or equal to the input x. And now Flux is complaining about this branch, saying that the post condition couldn't be refined. So this is pretty weird, right? You might have to scratch your head and look at this, and you'll realize, for example, if you take an 8-bit signed integer, the possible values that could have ranges from negative 128 to positive 127. So if you pass in the smallest possible I32 here, then this is not going to perform correctly. So we could refine this to say that actually x is not equal to, well, I'm typing with one hand, but I've typed it here. You can say x is not equal to the minimum I32, and now the refinement passes. So you can see the development process is basically just adding type annotations to functions. And this is a form of refinement types called liquid types. So we're adding types plus decidable logical predicates. So these predicates are basically what I showed you. Like that x is greater than 0. And you could have an arbitrary number of predicates there. Like you could put and then x is not equal to 5, and you can write whatever you want there. So one other thing that I won't show here that you could refine is you could refine some internal data structures or some data structures you're using in your program. For example, maybe you're indexing into some data structure you have. You could refine that to express that indexing will never have an out-of-bounds error. Because you can still, if you're using the bracket operator in Rust, you can still have an out-of-bounds error. So you might want to know at static time, at compile time, that you can't have a out-of-bounds exception in your code. Because, I mean, safe Rust is defined, but sometimes the defined behavior is panicking, and that's definitely not what you want. So we're going to take a look at something, maybe these are like interesting toy examples, but let's look at what we're actually working on in talk. So this is in-progress work. Well, first let's take a look at what the bug is. So there's a motivation for this. This was one of the most serious bugs that has been found in talk. And in general, bugs are sometimes very difficult to find because you first need to imagine what the bug could be before you test if this is a real exploit or not. So there was this issue that was found in talk where if you have some, like there's a huge issue for this, where, so the way memory protection works, again, is that we have an MPU that has ranges. So let's say we have process 1 running. Process 1 needs access to its whole heap and stack. So this entire range will get put in one MPU slot. Then if you want to do some IPC with process 2, or everything that's not expressed here is denied. Any memory access is outside of this. So we need to enable that also. But if you context switch to process 3, right, we've replaced this blue region with this orange region. Now we forgot to invalidate the second MPU entry. So now process 3, if it knew this, it could try and access this IPC region and access another process's memory, breaking the isolation guarantees of talk. So this was motivation for some of the formal verification work we're trying to do. So I'm going to try and give you a high-level explanation for how you would approach proving something like this. We're still working on the formal model, but this should give a pretty good idea of what it would look like to verify an abstract property with Flux. Like this absolute value and these other things, you could easily do the same thing with a runtime check. And okay, that will cost you some runtime, but that's not the end of the world. But if you wanted to express something like a process can only access exactly the memory that the process is given access to, then that's really hard, because then at runtime you would have to do some kind of exhaustive search by trying to access every memory address and then checking if the process can access everything in its own region and it cannot access everything outside of that. So you might try fuzzing, but fuzzing, again, has no guarantees it would find a bug like this. So this issue stems from the problem that the OS and the hardware's view of the world is different. So one thing you could do is you could make a struct of the regions that are enabled. So I don't want to get caught up in the Flux syntax, but basically this is just making it so that we can refine these two variables. So in the diagram I had 4 regions, but here we just have 2 regions, and these are either true or false for if they're enabled or not. So we want to make sure that a process can only access whatever it has been set for it, and there's not stale entries in the MPU config. So we might think about what the code was doing before, which is that it's just given some entries, some number of regions that it needs to write, num regions, and then it's going to just write these directly to the PMP is the RISC-V term, because that bug was for RISC-V. But it's the same thing as an MPU. And we might refine this. Again, you can ignore some of the Flux syntaxes, but this should be pretty clear that this is ensuring that the PMP, if the region needs to be set, then it matches the value that it should be. And Flux should be surfacing an error here. Maybe I messed something up in another file, but basically if we uncomment these 2 lines, then the refinement will pass, because we forgot to nullify the extra entries, right? If you had set 0 num regions, then you might still have 2 regions enabled. So that's a bug that would be extremely difficult to find if you're not using verification. So this has been really simplified. Again, we're working on proving something stronger, like that the union of every NPU region is exactly the same set as the union of every block of memory that the process should have access to. So that means we're refining this data structure that we're writing to registers of the PMP, and we are refining this to the actual RISC-V spec that you can only write valid entries that make sense, that are properly configured, and that this is going to match exactly the arrays or the ranges that the process has. So, okay. The problem with this thing is that I wrote this spec knowing what the bug was. So just as an idea of what it would mean to show that the unions are the same is we could write a high-level function where we're just asserting that this returns true. So this is just like we're writing normal Rust code, but this is an unused function that's going to get completely compiled out. Basically, we're just saying that for any config, if we call configure, right, these are just unbound configs, this could be anything, then the number of enabled regions should be the same as the number of regions that it has been called to set. So this, again, is really general. If you were writing something like this, you wouldn't even have to imagine what kind of bugs it would catch. This will just verify that when you compile with Flux that this is going to always be true. And I just wrote a little helper function to help with that. So that's pretty neat. Again, this has been dumbed down. Flux can solve all kinds of issues. Like when I was writing this code, I forgot that num regions is only valid for between these ranges. So if I was live coding, then it's really useful to have Flux surface errors while I'm coding. Compared to if I was writing unit tests after I developed this code, I might have to refactor my code to deal with some logical error I've done with my structure of the program. And same with fuzzing. Fuzzing might catch bugs long after I've finished developing the code. So Flux is going to surface these errors quickly. It's part of the Rust type checker. It's basically an extension of the compiler. And it's very easy to use. You're just adding type signatures. So just conceptually, you can think of it as an extension of the type system. So in summary, we already solved these 4 issues. Rust is making undefined behavior completely explicit, so the developers can minimize this. Faulty capsules are not going to compromise the integrity of the system, and concurrency is completely avoided. And lightweight verification is going to allow us to look at specific properties, right? Because we don't want to spend a ton of effort writing an OS from scratch that's completely verified. 'Cause that will take a long time. You need a lot of expertise for that. And we already have all this great existing code that we know is pretty much, or is almost correct. So we can go in and prove specific properties, such as memory isolation. And then we know that no code will ever violate this. And we haven't gone out and rewritten the entire MPU code. We only looked at the one configure function, and then after a context switch, that yes, the config is valid after every context switch. So that now we know that's an invariant of our system. And lastly, if you are using these Flux checks, now it's really hard for an attacker to try and push a malicious patch and try and break this, because Flux will surface the error, and this is not going to get accepted. So it makes it much easier to understand what your system's actually doing rather than what you think it's doing, right? You might think that for the absolute value example, that it would be acceptable to just write a comment that says, please don't call this with i32 min. But that doesn't actually solve the problem. Here, Flux would have pointed out every place you're calling a function that could violate the assumptions, and it saves you from that. So TalkOS is open source. You can check out the verification mailing list or contact us. And Flux is something that's in development, where our verification work is leading us to design and change how Flux works. And I'll be posting the slides online, and if there's any questions, I'll post answers at that URL.
Hi, I have a question. How does Talk compare to Oxide's Hubris OS?
Yeah, so I wasn't around with Talk when Hubris was being designed, but I do know the people at Oxide reached out to Talk, and they were interested in using Talk, but I think for them, they wanted to go with an all-Rust system. So Talk allows you to write C user apps, but the Rust bindings for system calls is not as well developed. And also Oxide wanted some more, I guess their use case is more specific, so they have a lot of money. They have money to make their own OS, and they don't need things like dynamic process loading. They just want to compile everything and know that exactly our processes are being run. So I guess they just wanted control. I'm not sure that there's a real trade-off or a real technical design decision, but yeah.
So I had a similar question, and I'm not extremely familiar with Hubris. If I remember correctly, they are using message passing and memory protection, even though everything is statically allocated and decided at compile time. At runtime, they still isolate using MMU features. And if I got Talk right, that's something that you do not do for capsules. So
Right, well, capsules are written in Rust, so we know they're memory safe, so you don't need to use the MPU.
I mean, at least in the case of Hubris, they still decide, even though they write everything in Rust, they still decide to isolate because you can have logic bugs, and if you have a logic bug, you still want hardware memory protection between your interfaces. Otherwise, any logic bug can be exploited to reach out to memory of your statically compiled binary.
Sure. I'm sure you could add that to Talk if you wanted to.
Any more questions?
Yeah, yes. So here. Is Flux able to catch panics? So like prove that there are no panics happening in functions, or?
So I think you could use Flux to do that. You could have some invariant that makes sure that branch would never be hit, but we haven't tried doing that yet.
Okay, thank you.
Any more questions? Okay.
But in general, with Flux, you're trading some of the power that you would have with other verification systems for the ease of use. In all other verifiers, you can't incrementally verify the code that you already have.
I wanted to ask, how does Flux prove preconditions on runtime values that the compiler cannot decide? Like you had the one example where you called the function with a negative value, but what if that value isn't decided until runtime?
Yeah, so that's a great question. I'll give a very abstract explanation of how Flux works. Basically, Flux is taking the intermediate representation of your Rust code, and it writes out it expands out the logical constraints and then passes that to an SMT solver. So if we look back at let's try type checking this absolute value function. It's the exact same one. Let's type check each branch. So the X is an I32. 0 would have this type signature in Flux. So Flux knows that the type signature of this is true if X is less than 0. Then you have two branches. So if this is true, then the return type of this entire function is not an I32. You have something more specific. It's this. And otherwise, it's just X. So Flux is going to expand this out. So we can just substitute all of these. The return type of this entire thing is an I32. But if X is less than 0, so if we take the first branch, then that implies that, and otherwise it's this. So then Flux is going to take this and first we would see, first we need to remember our type signature for this is that X is positive, this output is positive. So we need to check, is the type that Flux found a subset of the type that we asked for, which is non-negative numbers. So Flux is going to take all these constraints. It uses horn clauses, and it does a bunch of fancy things in the background, and then asks an SMT solver to provide a counterexample if there is one. Otherwise, we've satisfied it. So that's the high level. Basically, we're looking function-wide. Our Flux is modular, right? You're looking at one function at a time. And it's going to ask, is this output type a subset of the output type that the programmer has written that has annotated this function? So that's one of the reasons Flux is very fast, because let's say inside of abs, I had called a function, like I had called have here. Then Flux doesn't need to check inside of have. It already knows that we've annotated that with the output type of have is whatever it was, like a positive number that's smaller than the input. So it'll just substitute that in for the type and continue along. Does that make sense?
Yeah, but so what about the precondition checking? Like you had an example where you called a function that couldn't have the most negative number as an input, right? And then it found that. But what if you're calling it with an argument where the compiler cannot know whether it's in that class? Does it just fail? Or?
Yeah, so right here we have like a user input. If this entire function was just returning have of X, then, or one thing is that you have to annotate the types of everything in Rust. So the compiler already knows that this is some unbound I32. So if Flux needs to check that this has the constraint that it's not I32 min, then that's going to fail the type check. But also another interesting note is that you might be passing mutable variables. This is not a great slide, but basically the reason this is in Rust is because Rust's type system forces there to be only one mutable reference to a variable. So that makes it easier for Flux to keep track of what the values inside of structs are and things like that. But I think in general for preconditions, it's no different than normal type checking. You're just doing the exact same process.
Okay, but doesn't that get cumbersome? Like, because most of the time you probably don't have constraints on input values that get passed in from somewhere else, right? So don't you want to do a lot of cases where you know the value is going to be fine, but the compiler doesn't or something like that?
Yeah, but do you know it's fine? Like, I don't know.
Okay, so,
I think the solution to that would be, you'll say, okay, I give up on trying to verify this. I'll just put a runtime check.
Okay.
So if you write an assert x is positive, then now Flux knows that x is positive. Otherwise, the execution won't reach this line. Then you're sure that this invariant holds and Flux will be happy. But otherwise, the intended use is that you would actually verify downstream all the usages of this function to make sure they're actually correct.
Okay, thanks.
But I wonder for Talk project, does it have any user application, user space processes bundled as part of the project?
So I think the answer is no. Talk doesn't come with things that are run as apps. But we do have, as I mentioned earlier, Talk has a policy of not allowing any external dependencies. So one thing we did was we ported OpenThread to TalkOS. And that's not allowed to go in the kernel because, for one, it's not memory safe. It's not written in Rust. And also, it's a huge amount of code, maybe the hundreds of thousands of lines of code that we don't want to have to trust and put in the kernel. So in order to enable thread applications for working on Talk, OpenThread runs as a user app. And then these processes can just do IPC like any other OS.
Okay, thank you.
Hello, here. So how will Flux compare to alternatives like Prusty or Verus, for instance? Are there any trade-offs that you've made when designing it?
Yeah, so for Verus, we were considering using Verus at some point, but the problem is that Verus doesn't support all of Rust. So I think in Talk particularly, there's a lot of dynamic traits which Verus doesn't support. So we wouldn't be able to verify anything practical at all. And for Prusty, the Flux paper has some comparisons to Prusty. I don't have it up, but basically, I'm not sure exactly how Prusty works, but I do know that Flux is much faster because of the way it works. I think Prusty has existential types or something like that, which means that if you're doing the verification, it can take minutes, even for a small code base. Whereas Flux is going to run in maybe under 10 seconds, even if you have hundreds or like 1,000 lines of proof. So that makes the development process much better. And also, I think if you're verifying things with Flux, it's maybe slightly less lines of code you need to annotate things with.
But you think you'll be able to prove the same properties that other provers can? So Flux will be faster, but still have the same potential than Prusty, for instance? Or are you making trade-off there?
You are making a trade-off. I'm not sure about Prusty, but yeah, I don't know much about Prusty, but I know Verus is definitely, you can prove stronger things. So you can think of Flux, I've stolen this slide, as somewhere in the middle between testing and full verification. You don't need special expertise in understanding how formal methods work to use Flux. And you can statically check critical properties, so you might verify specific parts of your code, such as crash safety, but you're not going to be able to verify arbitrarily complex things like you would if you rewrote your entire code base in Verus or something like that. So the main thing we're trying to shoot for is that formal methods have been around for a long time, but they're not getting adopted. So our thesis is that, or like SEL4 is one of the largest deployments of formal methods in the wild. There's billions of devices. But they took decades and churned out many PhDs in order to make it, which is not practical if you want to take existing code in the world and verify it. So we really need to reduce the cost of verification. So that's, I guess, the thesis behind Flux. And of course, if you're comparing to testing, then you don't get any guarantees with testing. Like, you can only prove the existence of bugs, you can't prove the non-existence of bugs.
Thanks.
Okay, we're sadly coming up to the end of the Q&A session, but I'm sure you can catch Sami outside if you have even more questions. And then thank you very much.
Thank you.